Chemistry 3102. We're going to be talking about experiments 3.2 and 3.3. Keep in mind that for both of these experiments, you're going to be doing parts A and B. So 3.2, you're doing part A and B, and 3.3, you're doing part A and B. 3.2, this is the wet part of the lab, where you're going to measure a boiling point of a known compound and an unknown compound. You're going to measure a refractive index. And then 3.3, this is the dry part of the lab. And this part is covered on the data sheet. And we'll talk about that towards the end of the lab lecture. So relationships between structure and physical properties, effect of structure on boiling point and refractive index. So we're going to look at things like boiling points and intermolecular forces. And so you're going to want to keep those things in mind as we take a look at these two experiments during this lab lecture. So what are we doing in the wet part of the lab? You're going to be measuring a boiling point and the refractive index of cyclohexane. Now, I'm sure that you all know the structure of cyclohexane, which is simply C6H12. We know what the boiling point of cyclohexane is at 760 millimeters of mercury, or sea level, and it's 80.7 degrees Celsius. But what we're going to do is we're going to measure the boiling point in the lab here in Colorado Springs. And our thermometers are not going to read 80.7 degrees Celsius, will they? Because we're at a higher altitude. And so not only are we going to measure the boiling point, but we're going to have to apply a correction factor for temperature. And that is with respect to our thermometer and also for atmospheric pressure, since we're at a higher altitude. Then we're going to measure refractive index, and the refractive index only has to be corrected for temperature. Refractive index is not going to be affected by atmospheric pressure. And of course, you are expected to read the background for this experiment, which is technique D, which deals with boiling point, and technique E, which deals with refractive index. And you should have read that before coming to the lab lecture today, but hopefully you have to read that before coming to the lab and performing the experiment. So you're going to determine the identity of an assigned unknown compound by using the boiling point and refractive index. Now, when we have an assigned unknown compound, the number of your unknown is going to be written on the sash of your fume hood. There are roughly 5 million organic liquids in existence, but on page 191 of the lab text, we only have 24 unknowns on there. So we don't use all 5 million. We limit it to only 24 possible compounds. So in experiment 3.3, where you're going to be looking at both boiling point and refractive index, you're going to examine the tables 3.3-1-2-3, and you're going to use those to explain the trends of boiling point and refractive index. This, again, is the dry part of the lab. So this is the dry part, experiment 3.3, and this is going to be covered on the data sheet. Again, this is the dry portion. Now let's talk a little bit about boiling point, because you're going to boil cyclohexane in the lab, and you're also going to boil an unknown compound in the lab. Excuse me. If we think about physical properties, things like densities, melting points, well, boiling point is in those type of properties, namely physical properties, and we can use a boiling point to identify an unknown compound. All we do is measure the boiling point of our unknown, and we compare it to the known boiling point. And therefore, again, we can use that as a tool to identify an unknown compound. It also tells us a little bit about the compound's purity. Well, what is boiling point? The boiling point is of a liquid is the temperature at which the vapor pressure is equal to atmospheric pressure. Now, if we think about a liquid down here in our beaker, we know that the liquid is going to evaporate, a little bit. Let's say we're talking about water. If you put a glass of water out on a table overnight, and then you came back and looked at the level of the water, what would happen? The level of the water would decrease. Did you boil the water? No. If you just left it on a table overnight, you didn't turn you didn't heat the water up to boiling point. You didn't heat it up to 100 degrees Celsius. But you know that even at atmospheric pressure, that some of the water molecules have enough kinetic energy that they were able to escape the liquid phase and go into the vapor phase. The amount of pressure that these water molecules that are going from the liquid phase to the gaseous phase exert at atmospheric pressure, we call that vapor pressure. And so if you think about a liquid like gasoline, gasoline evaporates very quickly at room temperature and atmospheric pressure. And so something like gasoline has a high vapor pressure. It's got a low boiling point. It doesn't take a lot of energy to break the intermolecular forces that hold molecules of gasoline together. Whereas if you have something like oil, let's say you had motor oil, well, motor oil has a really low vapor pressure. If you were to leave that out for a long time, you'd see very little change in the volume of the liquid because very few of the molecules will have enough kinetic energy to escape from the liquid phase into the gaseous phase. So vapor pressure, high vapor pressure means we have a low boiling point. Low vapor pressure means we have a high boiling point. Right, and what are we doing? Again, and I'm repeating myself here, but we're going from a liquid to a gas, right? From the liquid phase to the gaseous phase. And we need to apply enough energy to enable the liquid or the molecules in the liquid phase to overcome their intermolecular forces to gain a pressure that is equal to atmospheric pressure. And that's what a boiling point is. So let's talk about intermolecular forces a little bit more. I know that most of you are enrolled in Chemistry 3101 with me, and we talked about intermolecular forces way back in Chapter 1 of that class. Also, all of you have passed General Chemistry 1 and General Chemistry 2, wherein you would have also discussed intermolecular forces. So boiling points are directly affected by intermolecular forces. If the molecules in a liquid phase are held together by weak forces, that means their boiling points are going to be lower. Examples of weak intermolecular forces are things like dispersion forces. We usually call these London forces. These are transient forces or fleeting forces. They're they are a result of a temporary dipole that is experienced between two molecules. If we increase the strength, if we look at molecules that have a permanent dipole, we can have dipole-dipole forces, which are going to be a little bit stronger, but neither of them are as strong as the intermolecular forces that are a result of hydrogen bonding. Now, hydrogen bonding is not a type of covalent bonding. It is simply an intermolecular force. However, it is so much stronger than London forces or dipole forces that we call it bonding. So stronger intermolecular forces, what does that mean? If molecules have hydrogen bonding, they're going to be held together more tightly than molecules that only have dispersion forces. It's going to take more energy to break those molecules apart in the liquid phase and separate them into the gaseous phase. Therefore, the stronger intermolecular forces that compounds experience, the higher their boiling points will be. So when you're doing part 3.3 of the lab, or the dry section of the lab, when you look at page 195 and you're comparing the compounds in tables 3.3-1, 2, and 3, you want to ask yourself, what are the intermolecular forces that are experienced between the compounds in those tables? And you're going to use those intermolecular forces to help you explain the boiling point trends. And those compounds and their boiling points are also in the data table, or the data sheet, and we'll look at that at the end of the lab lecture. The definition of the boiling point, again, is the temperature at which vapor pressure of the liquid is equal to atmospheric pressure. But we know, especially we who live in Colorado Springs, that boiling point depends on atmospheric pressure, doesn't it? At sea level, atmospheric pressure is 760 millimeters of mercury. And a millimeter of mercury is the same thing as a torr. And I'm sure you've all heard about the famous experiment done by Evangelista Torricelli down by the seaside, where he inverted a capillary full of mercury into a dish of mercury, and he measured the height of the column of that mercury and found that it was 76 centimeters, or 760 millimeters, at sea level in Italy. But we know that in Colorado Springs, the boiling point of water is not going to be 100 degrees Celsius, which would be the boiling point of water at sea level. Could anybody tell me would you expect the boiling point of water in Colorado Springs to be higher than that at sea level or lower than that at sea level? Does water boil at a lower temperature in Colorado Springs than it does at sea level? Yeah, it boils at a lower temperature. Okay, good. At least my students are on the right path there. Yeah, at a higher elevation, the water or any liquid is going to boil at a lower temperature, and that is due to less atmospheric pressure pushing back on the molecules in the liquid phase. So if we lower the atmospheric pressure, then we're going to have a lower boiling point. I can go into more detail on that, and I might talk to you a little bit more about that at the end of the lab lecture if there's time. So when we measure a boiling point in our lab, we have to correct that boiling point to atmospheric pressure of 760 torr or 760 millimeters of mercury, or 1 atmosphere, but the atmospheric pressure at what? At sea level. And we are pretty far from sea level right here. All right. Well, if we correct our boiling points to 760 millimeters of mercury, then it doesn't matter what the local pressure is when we measure our boiling point, because we're going to do a correction and we're going to report a corrected boiling point. How do you correct a boiling point? Well, you use this thing here that we call a nomograph. And there's a nomograph in our textbook on page 29. So using the nomograph, we can estimate boiling points at various pressures. How do we do that? What we're going to do is we're going to connect a straight line, and I don't have a ruler, and I'm not sure how to use this function on the iPad. You'd think, maybe I could do it. Anyhow, I'll see what I can do here. Anyhow, what we do is we connect a straight line between the normal boiling point. So there's my highlighter here. We have the normal boiling point over here. So this is normal boiling point at sea level. And we connect it with the atmospheric pressure of where we are. So if we're in Colorado Springs, we're going to be at a lower atmospheric pressure. So what we would do is we would connect the two. So we have our normal boiling point. Let's say we're boiling water and we're in Colorado Springs. We're lower than 760, right? 760 millimeters of mercury would be up here, right? For our 100 degrees. I'm moving my ruler around the best I can, you guys. But if we look at our boiling point, which is 100 degrees Celsius, and let's say we're at Colorado Springs, let's say our atmospheric pressure is down here. Where's my 100? There we go. Then you see I end up crossing the delta T correction somewhere around here. And I'm going to explain what that means in a second. So here we go. This is the nomograph that you're going to use to correct your for the boiling point of your known compound and your unknown compound and the altitude at UCCS and the atmospheric pressure. If you're wondering what the atmospheric pressure is at Colorado Springs, well, atmospheric pressure can vary from day to day, and thus we will write down the atmospheric pressure on the board in millimeters of mercury. Depending on your instructor may choose to write the atmospheric pressure in different units, and then all you have to do is just a quick conversion if they decide to put it in atmospheres or something else. Anyhow, where was I? So that deals with pressure corrections. And if you're wondering, Mr. Dion, I'm not 100% sure on how to use the nomograph. Don't worry, at the end of the lab lecture or further along in these slides, I have a whole scenario where I go through not only a thermometer correction, but also a boiling point correction. So I'll show you how to use that. But before we get into that, I want to talk a little bit about refractive index. Now, this is something that's probably new to most of you. I'm sure that all of you have boiled water at some point in your life if you're making macaroni and cheese or something, but I could probably assume that most of you haven't taken a refractive index before. But I'm sure that you've all put, a spoon in a glass of water, and you've seen how the spoon appears to be bent in the water, and that is due to refraction. And that is essentially what we're doing here, except now we're going to be using our organic compound and we're going to be measuring the refractive index of the light that's passing through our organic compound. So what can we use a refractive index for? A refractive index can be used to identify an unknown compound, and it can also be a measure of the purity of a compound. And we're going to use refractive index to help us identify our unknown compound. So refractive index, a little bit of the theory. When we take light and we pass it from a medium that is less dense into a more dense medium, the light gets bent, or we say it is refracted. And so if we want to measure our refractive index, which we use the variable n, you see that you have the angle of incidence right here. So this is the theta right here, and I don't want to get into too much math, but this is our angle of incidence. So we have the light coming through the air like this, and when we go from air to a liquid, well, a liquid is going to be more dense than air, and so what it does is it's going to refract or bend that light, and then you're going to get an angle of refraction. So you get a new theta over here. So we could call this the theta of incidence and the theta of refraction, like that. But either way, they just call it I and R. So theta I really means just I, and theta R, just thinking about angles in my mind here. So when the refractive index is measured, you take the sine of the angle of incidence over the sine of the angle of refraction. Now, n is a unitless number, and it's always going to be greater than 1, since the angle of incidence light is always going to be greater than the angle of the refracted light as the light passes from a less dense to a more dense medium. Now, if we just do a quick, I was going to go over an example calculation, but there's no real need to do that. Anyhow, all of this treatment here, the light going from the air into the liquid, this is all done in the refractometer. Okay, and so this angle of refraction here, this depends on the identity of your liquid. All right, let's move on from there. So the refractive index in a given medium, and the medium that you're going to be using is your unknown as well as your known, is going to depend on two things. First thing is that it depends on the wavelength. We can control that pretty easily, right? All we do is we use electromagnetic radiation with a specific frequency. So the light that we use has this wavelength. It's 589 nanometers. I'm not going to ask you a whole lot about that. It's just one specific wavelength of light. It comes from the D line of the emission spectrum of sodium. And again, I'm not going to ask you a whole lot about emission spectra. You would have covered that in General Chemistry 1. So again, the light that's used inside the refractometer has this wavelength. Okay, so everybody has the same wavelength of light, no big deal. But the refractive index is temperature dependent. And the reason why it's temperature dependent is because you should also remember this from general chemistry, that the temperature is going to change the density of the liquid, isn't it? Right? What happens if we crank up the temperature, or if we increase the temperature of our liquid? If we increase the temperature of our liquid, then our liquid, or our medium, its density is going to decrease. Okay, let's see if we can connect some more dots. If we decrease the density of our medium, then the speed of the light is going to increase. As the speed of the light gets faster, then the speed of light in the medium is going to decrease, and then the refractive index is going to decrease as well. And so the conclusion that we can draw is that the refractive index is going to decrease as the temperature rises. And this is probably a point that you're going to have to come back to, later on. The refractive index N is going to decrease as the temperature increases. Now, when you measure a refractive index in the lab, we don't keep our labs at exactly 20 degrees Celsius, right? That would be impossible to keep the lab at exactly 20 degrees Celsius. So values of refractive indices that you see in the literature, or if you were to look in the CRC handbook, those refractive indices are reported to 20 degrees Celsius. So they're adjusted to 20 degrees Celsius. Now, if you're not going to be recording your refractive index at exactly 20 degrees Celsius, you need to make a correction for that. How would you do it? You're going to use this beautiful equation here, which you're going to be able to bring in with you, of course, to the lab. So the refractive index, the corrected refractive index at 20 degrees is equal to the refractive index that you measured at your temperature. So this is simply the refractive index that you read off the refractometer plus 0.00045 multiplied by the temperature in the room, subtract 20 degrees. So when you measure the refractive index of your compound on the refractometer, it's going to give you two values. It's going to tell you the refractive index to 4 decimal places, and it's also going to give you the temperature. So let's say you got these values for your unknown, but you wanted to compare them to the refractive index of a list of unknowns, but all of those refractive indexes are reported to 20 degrees. What do? You do the correction. Very simple math. I don't like to use the word simple in chemistry and combine them a whole lot, but I think it's a pretty easy easy mathematical maneuver here. We have -4 multiplied by 0.00045, and then we add that to 1.5523, and now we get our refractive index that is corrected to 20 degrees. Now we can compare it to a list of unknowns. Okay, the typical range for values of organic liquids, they usually range from 1.34 to around 1.56. They can be outside of that, but most organic liquids are going to be somewhere in that range. But again, with 5 million organic liquids, well, you can probably imagine that we can step outside of that range. Okay, anyhow, here's a refractometer. I know that all of you have spent some serious time taking melting points in the lab, and so you spent some time in the instrumentation room, and then you've probably noticed that we have refractometers. You might not have known what they are, but you've probably all seen these instruments here called the digital refractometer, which was originally developed by Ernest Abbey a long time ago. And I'm not going to ask you about the history of a refractometer, but I will expect you to know how to use the refractometer. Now, these are expensive and sensitive instruments, so we expect you to know how to take care of them properly. We have prisms in the refractometer, and I'll show you where the prisms are located in a picture in a couple of seconds. But we want to make sure that the prisms are always clean when they're not in use. So we always clean them with a tissue. Namely, we use what's called a CHEM wipe, which is basically a sterile type of tissue, and methyl alcohol, which is the same thing as methanol. Okay, and you clean them with a little bit of methanol on a CHEM wipe or a tissue very carefully. Okay, you don't have to be rough or aggressive with the refractometer. Never touch the prism. So that's it looks like a piece of glass. Never touch the prism with your fingers. Never touch it with anything that's hard. I don't think anybody would have a reason to do that. You always use tissues. Now, I'm sure you're like, okay, Mr. Dion, I can treat an instrument with care. I'm a careful person, and I would totally believe you. But one thing that you might not think would be intuitive is this last bullet point here, is that when the refractometers are not in use, so let's say you're using it and there's nobody in the room with you, you're just using the refractometer, and then you're going to walk away from the instrument. When you store the refractometer, in fact, if you were to walk into the instrumentation room right now and go look at any of the refractometers, you would see that they're always stored with a CHEM wipe, which is the same thing as a tissue. They're stored with a CHEM wipe between the prisms. Okay, so we always store them that way, and that is to maintain the integrity of the crystal and to reduce scratching or any imperfections that would be on that. So you can see that I'm going into care of the refractometer quite a bit. The reason why is because they're expensive and it's important, but trust me, it's very easy to do. So here's what you're going to see in the lab. Mr. Mayer or somebody's going to have left out some methanol. There will be a little pipette and a CHEM wipe. Okay. CHEM wipes were developed by I think it's the Kimberly-Clark Corporation. I had a friend who lived in Quebec who spent, I think, 3 summers planting trees in northern Ontario, which was basically experiencing a little bit of hell right here on planet Earth. And I remember he came to the lab one time with me, and he saw the CHEM wipe, and he said, "Oh, Kimberly-Clark, I hate those guys. I planted so many trees on account of those guys." Anyhow, I digress. Where was I? So we have the CHEM wipes, we have the Pasteur pipette. And the Pasteur pipette I said the Pasteur pipette. I might not have mentioned this. For the methanol, you can dispense it directly from this bottle, but for adding your sample to the crystals, you're going to use a Pasteur pipette. Anyhow, there we go. I think that I will probably do a little demonstration with my students, and I'm going to ask my instructors, my fellow instructors, if they just do a very quick demonstration. Doesn't take long at all, to show you how to use a refractometer correctly so that we can ensure that these instruments are around and in use for, I don't know, your children's children? Yeah. So here's the basic operation. And this is best seen rather than just simply read about, but I'll show you quickly what you do. You add 3 or 4 drops of sample, doesn't take a lot. If you have a volatile compound, right? If you have something that's got a high vapor pressure and it's going to evaporate really quickly, you might have to add a little more sample, or you might have to work faster so that there's enough sample when you close the prisms or put the prisms together. Then there's 2 knobs on the instrument. We have a coarse knob and we have a fine adjustment knob. What you do is when you look into the lens, and where is it? Or the eyepiece, okay? Right here, you're going to put your eyeball right up to there, okay? You're going to be looking in here. This is the coarse knob here, and this is the fine adjustment knob here. I have that on another slide, but I just want to show you quickly. You're going to adjust the coarse knob so that the horizontal line, which might not be sharp at first, it might be a little fuzzy, but it divides the upper light half and the lower dark half. You want them to be exactly at the center of the crosshairs. Once you've got it exactly at the center of the crosshairs, then you're going to use the eyepiece or the fine adjustment knob to get it to focus in so that everything is really sharp. Then you simply press the button that says, record refractive index, and you write it down in your lab notebook. So it is not difficult to run a refractive index. It literally takes seconds. Going back to our refractometer, this is the eyepiece up here. This is the coarse adjustment knob. This is the refractive index value screen. You're just going to read it off there. Mr. Mayer might be able to correct me on this, but I believe that you never turn off the refractometer. So I know it's a knee-jerk reaction for students to maybe think, okay, after I'm done with this instrument, well, I'm taking up electricity. Maybe I should just turn it off. Okay. We'll just write in here, do not turn refractometer off. Okay. That's not refractometer. Do not turn refractometer off under any circumstances. In fact, that can be a real annoyance to the lab coordinator and to the people that set up our experiments. So don't turn it off under any circumstances. I know that sometimes people might do that, just might be a knee-jerk reaction, but Mr. Mayer informed me that there's actually a sign above it that says it. So make sure you take that into account. Don't turn it off. Where was I here? So here's the prisms at the back. I'll kind of zoom in here, and you can see that we have a CHEM wipe in between the prisms, again, to maintain their integrity. So when you want to run your sample, you just grab this little lever here and you lift it up. It's kind of on a hinge. You put the sample on, you put the prism back down without a CHEM wipe in it, and then you press read on the screen. Anyhow, what is it going to look like when you look through the eyepiece? It looks quite a bit like this. It's pretty good. I mean, it's just a little cartoon that was drawn on the computer, but it actually looks quite a bit like this. This line at the midpoint here, we got a fancy name for that line. We call it the line of demarcation, okay? So the line of demarcation, you want to sharpen this line. So along this line here, you want to get it as sharp as possible. Then you're going to use the eyepiece to sharpen the crosshairs. It's one of those things that I find a little challenging to explain, but once you look into the eyepiece and you see how it's fuzzy and you see how you can adjust it, it becomes a lot more abundantly clear when you actually get to try it. And again, taking a refractive index is something that doesn't take long at all. Again, once you're done, put a CHEM wipe in between the prisms. If there's somebody right behind you just waiting there with, champing at the bit with bated breath to use it, well, then you could leave it open and let the next person use it after you have cleaned it. However, anytime you're not using it, make sure you have a CHEM wipe in between the prisms. What do I expect you to read before coming to the lab? Well, if you haven't done it already, I expect you to read Technique D, which deals with boiling points. I expect you to read Technique E, which deals with refractive index. A lot of good information in there. Then I expect you to read Experiment 3.2 A and B. This is the wet part of our lab. And then experiment 3.3 A and B, this is the dry part of our lab. And the dry part of our lab, this is covered in the data sheet, okay? So instead of getting our students to write out big gaudy conclusions and summaries, you've probably noticed by now that we usually ask some kind of probing question in the data sheet, and that is kind of our summary or conclusion for our experiment. All right, I want you to write in your lab notebook in blue or black ink. I prefer black ink myself, and in fact, yesterday I had a conversation with one of my students who was writing in blue ink. I couldn't disagree that the color was blue. However, it was some kind of seafoam or aqua or teal type of blue, and I said, that's not a real blue. So make sure you use a normal blue pen, the kind you might get at a notary or something. Anyhow, remember, format counts. I think that by now most students are pretty solid on what constitutes good formatting, and they're cognizant of that when they put their labs together. So what do you need before you step into the lab? Next week or the week following, you need to have a header. Make sure you put the title of the experiment, put the complete title on the first page. An abridged or an abbreviated title is acceptable after the first page. For the purpose, make sure you include both parts, 3.2, which is the wet part of the lab, and 3.3, which is the dry part of the lab. You know, questions that you want to ask yourself. I shouldn't have to do too much hand holding in terms of writing a purpose at this point. You know, you want to think about, what are you doing? Is there any isolation or purification? Well, not in this lab. And what are you identifying an unknown? Absolutely you are. You're going to be identifying an unknown, and you would want to mention how you're going to be identifying that unknown. I have some good news about your table of reagents because there's only one compound in the whole thing, okay? The only compound that you're going to put in there is cyclohexane. Yes, I know that there is a big list of possible unknowns on page 191 in your textbook. Do not put all those unknowns. Again, I believe there's 24 of them. I mean, you could put them in there, but that would be a lot of extra work, which is totally not required. Either me or your lab instructor will have the list of unknowns in the lab. I might print them out or something so that my students can refer to that while they're in the lab, since we don't want you guys bringing your notebooks or your lab textbooks into the lab. So again, we'll have that list there so you can refer to it right away. You measure your refractive index, you do the correction, you can go right over to the sheet and say, hey, does this make sense? Does this look like something that might be one of the possible unknowns? Also, be sure to include the safety hazards. You just look at the chemical list, which is on Canvas. Make sure you include a source. And when you're writing your procedure, be sure to do the 2-column format. Where are you going to get your procedure? Well, it's going to come from this lab lecture, partially. The slides where I discussed experiment 3.2 A and B. So measuring a boiling point, measuring a refractive index, and also there's some information on page 90. Make sure that you have enough detail in there such that another student could pick that up and be able to repeat the experiment, and also be sure to leave space for your observations. So again, what are you going to do? You're going to be measuring the boiling point and the refractive index of 2 compounds. A known compound, which is going to be the same for everyone, it's cyclohexane. And you're also going to measure the boiling point and refractive index of an unknown, and you're going to identify that unknown. Again, I told you where the unknown compounds will come from, page 191. You want to record the atmospheric pressure or the ambient pressure in order to correct for the boiling point. You don't have to worry about this bullet point here. I'm just going to cross this out, making a whole temperature versus time plot, not required whatsoever. And then be sure to record the temperature from the refractive index instrument in order to make your calculation for refractive index. This is something that could be a big boo-boo if somebody was to do this. I've only seen a student do this once. Okay, and it was when a student was trying to work really quickly. The student measured a refractive index, wrote it down in the notebook, and then ran back to the lab. And then it was towards the end of the lab, and the student just kind of took off. And, you know, the student had forgotten to write down the temperature that was reported on the refractometer. And so the student wasn't able to do the correction properly because they didn't have the proper or the correct temperature. So something to think of. With respect to the boiling point setup, you might be wondering, you know, how am I going to boil something, Mr. Dion? Do I just throw it in an Erlenmeyer flask with a boiling stick and just let it rip, potato chip? No, no, we have a nice way to measure boiling points in the lab. In fact, there's a couple of ways of measuring boiling points in the lab, but the way that we're going to do it is we're going to use what's called a Craig tube, which comes from your lab kit. You've probably all noticed these little metal blocks that are in all of the labs, in all of the fume hoods, excuse me. You'll see that there's one for every hot plate, so you'll have two in your fume hood, but you just need one. So you need a heating block, then of course you need a hot plate. Everybody knows what that is. You guys remember what a burette clamp is? From General Chemistry 2 probably is where you would have mostly used a burette clamp when you did titrations. So instead of holding your thermometer with a 3-finger clamp, no, you hold it with a burette clamp. If you try to hold it with a 3-finger clamp, those things have so much torque that you could probably snap the thermometer, which could cause a serious accident, because if there's one thing we don't like to mess around with, it's broken glass, okay? Some of the worst accidents I think that happen in undergraduate labs happen oftentimes with thermometers. When I was an undergraduate student, we did an experiment where we were measuring a boiling point, and we had to put a thermometer through a rubber stopper that had a hole in it. And so the student was trying to poke the thermometer in there, and you were supposed to add grease to it. And I can't remember if the student didn't grease it or if they had, if they had bored the hole themselves using a boring kit, and if they'd used the wrong one or something. I don't know. But anyhow, the bottom line is they ended up putting a thermometer basically through their hand, which is really nasty. So also, we'll have an experimental setup in the lab for you to kind of show you exactly how it's done. So here it is. At the bottom of your Craig tube, you're going to need a boiling chip. The Craig tube is just too small to have a boiling stick in there, so you're going to use a boiling chip. I know that my students, I usually don't ask them to use boiling chips, so this is your first chance, if you're my student, to use a boiling chip probably. Anyhow, and we do that to reduce what's called bumping. Also, you'll notice that there's a few different little holes or indentations in your heating block, and you use the one that isn't drilled all the way through. So there's only one that doesn't have the hole, or no, that's not true. It's the small one that isn't drilled all the way through. Anyhow, it should be pretty obvious which one it is. Okay, now the way that you set up the thermometer is very important. And this is something that your lab instructor may come around. I like to walk around and see how everybody's, setup is going. How's this person doing? How's that person doing? And the height at which you set the thermometer above the liquid is quite important. Okay. Now it says here, place the thermometer bulb just above the liquid, but not in the liquid, because you want to measure the temperature of the vapors. The bulb can't touch the glass sides because that's going to affect your temperature reading. You won't be measuring just the vapors of the boiling liquid. And the liquid level will be just above the heating plate. So again, I think that what I'll do with my section is I'll make a setup, and I'll show you what the level of the liquid should be. And I'll show you, how high the thermometer should be from the top of the liquid in order to get a good boiling point. Another thing that you can do, because you're going to be in a lab, there's lots of air flowing around, especially in a fume hood. You've probably noticed there's a lot of air moving in an organic chemistry lab. And so you can just take a little piece of aluminum foil and wrap it around the Craig tube. And what that does is it creates an insulation, which just makes it easier to boil the liquid. It says here it's not required, but if you're having a hard time getting it to boil, it might be a good idea to do that, to set up a little window like that. And I've done many distillations in my life where I had to insulate, with glass wool and all kinds of different things, heating jackets and whatnot. Anyhow, that's neither here nor there right now. Why use the burette clamp? Well, the reason you don't use the 3-finger clamp is because I would probably be the first guy to snap a thermometer, and that is not a good thing. What do you set the hot plate setting to? Well, for a known, remember that we generally set it to 1.5 times the boiling point. As far as your unknown goes, I want you to discuss that with your lab instructor. So you're going to discuss that in lab, where you should start heating. Because I don't want anybody to just start and say, well, I'll just jack my hot plate up to the highest setting, it's going to boil no matter what. Well, no, I don't think that is a good strategy. So in the lab, your lab instructor will go over what a good strategy would be and kind of go through a little discussion with you on what a good strategy would be for boiling your unknown, since you don't know the boiling point. What else? I've covered the last two questions. How do you know when you've hit the boiling point? That's a good one too. Okay. You know that you've hit the boiling point when the temperature is stabilized, right? You're measuring the boiling point. You might see boiling and you might be forming vapor, but if the temperature of the thermometer has not stabilized, you have not reached the boiling point. So you want to make sure that the temperature has risen, but then it remains stable. Now, if the temperature is stabilized and you jack up the temperature of the hot plate, let's say by another, I don't know, 30 degrees Celsius, and this would also be something to discuss in the lab. If you turn up the temperature by another 30 degrees Celsius and the temperature of the vapors does not increase, therefore your boiling point, what you're measuring on your thermometer, doesn't go up, you'll know for sure that you have reached the boiling point. So you need to calculate corrected values from your measured data for both the boiling point and the refractive index. Refractive index calculation, a little simpler because you're just using a quick formula. But for a boiling point correction, we need to correct not only for atmospheric pressure because we're in Colorado Springs and we're going to use the nomograph for that, but we also need to correct for the error in our thermometer. Yeah, something you might not have thought about. I know that all of you have thought about the fact that, well, I'm in Colorado Springs, so my boiling point isn't going to be the literature value. It's not going to be the value reported at 760 millimeters of mercury. But think about it. The thermometers that we have in all of our drawers, those thermometers aren't cheap, but they also don't cost, $10,000 a piece or something. So there's going to be some error in those thermometers when they're made in the factory. So the amount of error, and depending on whether it's, measuring the boiling point too high or too low, or the temperature too high or too low, is going to vary between the thermometer. So everybody will probably end up with a slightly different thermometer error. It could happen that two students would have the same thermometer error, but I would say it's unlikely. And that's another reason why we leave thermometers in your drawers instead of just putting them on the bench or something. Because think about it, if we left thermometers in a drawer that was communal, like the clamps or Buret clamps or something, that means that any week you could just go in and grab whatever thermometer you want, right? And that means that you'd be getting different errors in your, temperature readings every week. By keeping the same thermometer in your drawer week after week, that means that once you've calculated the error in your thermometer, you could use that for another lab where you calculate another boiling point. Something to think about. Anyhow, let's talk about how we do a thermometer correction. So they're kind of listed in reverse order here, aren't they? Right? The first thing you would do is you would do the thermometer correction, after which you would correct for pressure of your unknown, okay, or correct for pressure when you're measuring a boiling point of your known or unknown. If you're not following me, let me show you, okay? So if you're not awake right now, or if you're, kind of turned me off, which is totally normal. I was a student for a long time. I know what it's like to be sitting in a class on a Friday afternoon at 1 p.m. Your liver is working really hard, maybe after eating a big lunch or something, and your metabolism is just cranking here, trying to digest your food. Anyhow, I need you to wake up for a few minutes and follow me on this slide and on the refractive index correction as well. So this is going to be really the answer for how to do your calculations in the lab. Now, what you're going to do is you're going to convert the lab pressure to millimeters mercury. Your lab instructor is going to use the lab's barometer. Yes, we have a barometer, and we're going to measure the atmospheric pressure. Like I said, atmospheric pressure varies from day to day in Colorado Springs. But let's say, for example, the atmospheric pressure during the lab, let's say it was exactly 606.8 millimeters of mercury. That's the observed pressure, right? 606.8 millimeters of mercury. Now let's say that we know the literature value of our known is 69.0 degrees Celsius. Let me get a different color pen here. So we know that our known boils, if we look up the boiling point of our known, it boils at 69 degrees Celsius. Okay, So you go ahead and you measure the boiling point of your known. The 69 degrees Celsius is not what you're looking at here. You want to put down on here what your boiling point was, which is, sorry, my mistake. You have 69 degrees Celsius on here, okay? So if you're at 69 degrees Celsius for the boiling point of your known, and your atmospheric pressure is 606.8 millimeters of mercury, you see that you cross the nomograph on the correction scale at 5.7 degrees Celsius. What does that mean? Okay, well, what that means is that you're going to correct for the atmospheric pressure by 5.7 degrees Celsius. Now, what you measured was 65.7 degrees Celsius. Since you measured it at a lower atmospheric pressure, what would you have to do to this correction? What would you have to do to that correction factor? You have to add this correction factor to your measured boiling point. Now, did I calculate it in here? Yes. So overall, if you tally these two numbers up, you get 71.4 degrees Celsius, right? Now, look, we're just talking about the nomograph correction. Based off of the nomograph correction, it tells you that you want to add 5.7 degrees Celsius, which you add to what you read in the lab. That gives you 71.4, but you know that the actual boiling point of the compound is 69 degrees Celsius. What do? You end up, you subtract your, son of a gun, you subtract, move it up like this, you subtract your corrected boiling point from the literature boiling point, and you get negative 2.4 degrees Celsius. What does that tell you? That tells you that once you did the correction, and this is what I'm trying to get to, you ended up with a boiling point that was 2.4 degrees Celsius too high. So that means that when you measure your boiling point of your unknown, what are you going to have to do? You have to do the nomograph correction, but you have to subtract 2.4 degrees Celsius because this is the error in your thermometer. It measures 2.4 degrees Celsius too high. And that was kind of a roundabout explanation of what I was getting to, but if I could, give you the quick and dirty explanation of what's going on here is repeating myself. You have the boiling point that you measured. You get the correction factor off the nomograph. It tells you that you have a boiling point of 71.4 degrees Celsius. It's not correct. You know the actual boiling point is 69. So you subtract the 71.4 from it and you get negative 2.4. You apply that negative 2.4 to any of the boiling points that you take with that particular thermometer. Okay, kind of a roundabout explanation. But now this is how you're going to correct for the boiling point of your unknown. So this part of the experiment you're going to do with your cyclohexane, right? You're going to determine the error in your thermometer or your thermometer correction using the cyclohexane. Now you can use that negative 2.4 or that understanding that your thermometer reads 2.4 degrees Celsius too high to determine the actual boiling point or the boiling point of your unknown atmospheric pressure. So follow along with me again. Again, the atmospheric pressure hasn't changed. We have our unknown. We measured a boiling point of 124.1 degrees Celsius. So we are at 124.1 degrees Celsius right here. We cross the observed, our actual pressure, and we get a correction value of 6.6 degrees Celsius. You're at a higher altitude. So what would you have to do? You would have to add 6.6 degrees Celsius to the boiling point that you measured for your unknown. Now I added that up. What does it give you? 120, no, that would give you 124.1 plus 6.6. This would give you 130.7 degrees Celsius. If you were to walk over to the list of unknowns and compare this, for example, to the list of unknowns, it would be incorrect, right? You did the nomograph correction properly, right? You figured that you have to add 6.6 degrees Celsius to your boiling point, but you forgot that you've got to subtract 2.4 degrees Celsius from this for the error in your thermometer. Once you do that, then you have corrected not only for atmospheric pressure, but also for the error or the correction factor of your thermometer, and you end up with 128.3. Give me a thumbs up if you follow me on that, and if you don't, let me know and I'll re-explain it, or I'll. Anybody? Moira, you with me? Okay, good. My student's internet is working. Okay. So if you're having trouble making your correction, you're doing your thermometer correction and correcting your boiling point, you can always refer back to this. Now, your lab instructor is willing to help you to some extent, but we also expect you to be able to figure this out on your own using the nomograph. You know, maybe a question here or there, but the same procedure is going to be applied for every student. Okay, you all have the same unknown. You all are going to have different unknowns, but the correction is going to be done the same way. Okay, so for correction of a refractive index, much simpler. Just use the formula, which I showed on an earlier slide. And it's this formula here where we correct for the refractive index at 20 degrees Celsius. So let's say if you put your sample on the refractometer, you press the button, you read the refractive index, you record that in your lab notebook, you record the temperature, it's 21.2 degrees Celsius, you just plug the numbers in and you end up getting your correction. That's it. There you go. So you'd end up with a refractive index which changes by a little tiny bit from 1.3874 to 1.3878. There we go. So again, I've told you, I think 3 times where the unknown liquids are. They're on page 191 in the lab book. You're going to compare your boiling point and refractive index data with that table. You're going to be able to identify your unknown. I've done this lab many times. Students are usually able to identify their unknown pretty, I'd say with, I don't like to use the word easy in the lab, but I'd say usually students are able to figure out what their unknown is. You want to calculate the percent error for your boiling point and refractive index using this formula here. And then make sure you've cleaned everything up. I talked to Miss Herring, and she told me that one of her labs after the recrystallization made a total mess of everything and didn't clean everything up. I'm sure that's not you guys who are attending lab lecture, but be sure to clean it up after yourself, just like at home. In fact, my lab yesterday, some students left, you know, a little bit of a mess behind. So make sure you leave everything the way you found it. All right. Then you're going to work on the data sheet, which you complete, identify your unknown compound, complete the data tables for boiling point corrections, refractive index corrections, and let's take a look at what the data sheet looks like. So this is posted to Canvas, and I'm not sure if I posted it as a Word file or a PDF, but I'll try to post it as a Word in case anybody wants to enter their values using Microsoft Word. So what do we have? For your known compound, everybody has the same known compound, cyclohexane. It has a literature boiling point. You're going to measure the experimental boiling point. You're going to get the correction from the nomograph. Then you do the calculation to determine their thermometer correction. Your thermometer correction might be high and it might be low. So if it's low, you'd have to add. If it's high, you'd have to subtract. So it depends. Everybody can have a different thermometer correction here. But then you're going to measure the boiling point of your unknown. You're going to calculate the delta T from the nomograph, not calculate it, but you're going to measure the delta T from the nomograph. Then you use that and your thermometer correction to determine the corrected boiling point. Then you calculate the percent error for the refractive index. You have the literature value for cyclohexane. You put in your unknown. You measure the refractive index. You correct it. And there you go. Then you identify the unknown. So right here, you're going to identify your unknown or put your unknown number here, and then you identify what it is. So you spell it out. You don't just say it's unknown number 6. No, you write down what it is. So give us the whole name. Now, the dry part of the lab, 3.3 A and B. again, instead of me getting you to write out some kind of long and gaudy summary and conclusions, the questions that come at the end of the data sheet kind of take the place of that. Instead of getting students to just rehash the lab, which people are prone to do sometimes. So here are the questions that you have to answer for the dry part of the lab. This table comes straight out of your lab textbook. Question is, summarize the effect of chain length, the effect that chain length has on boiling point for the compounds in this table, and does the refractive index trend make sense? Well, you guys are all organic chemistry students. You know that when we go from pentane to hexane to heptane to octane to nonane to decane, what are we doing? We're increasing the length of a linear hydrocarbon, right? And what's the trend in boiling point? We see that boiling point increases as the length of the hydrocarbon increases. We also see that density and refractive index increase with the length of the hydrocarbon chain. So what I want you to do in this question is to explain the effect that chain length has on boiling point and refractive index, and rationalize the trends that you see in this table. The next question, question number 2, I want you to take a look at the boiling points of these branched alkanes. All 3 of these compounds, hexane, 2-methylpentane, and 2,2-dimethylbutane, they're all isomers of each other. They all have the same molecular formula, C6H14. However, since they're isomers, they have different boiling points, different refractive indices, and different densities. What I want you to do is to compare the linear hydrocarbon with the 2 that are branched, and I want you to compare the branched ones to the branched compounds' boiling points to the boiling point of hexane. What kind of effect, or summarize the effect that branching has on boiling point? And you can see that it definitely has an effect. I want you to explain the effect using the rationale of intermolecular forces for branched and unbranched alkanes. I also want you to explain how the refractive index trend makes sense, or rationalize the trend, I guess is what I should say. And then the last question deals with these compounds here, these 5 compounds. Take a look at these 5 compounds and explain how the functional groups affect the intermolecular attractions, or the intermolecular forces, IMFs. Now notice that the first one is hexane. There is no functional group here, right? An alkane does not count as a functional group, but in pentanone, 2-pentanone, we have a ketone. In valoraldehyde, we have an aldehyde, so pentanal, valoraldehyde. We have 1-pentanol, it's an alcohol, and then we have a carboxylic acid. You should be able to use your knowledge on intermolecular forces and how they relate to functional groups, or whether a compound is simply a hydrocarbon, and explain the trend in boiling point here. You see that the molar masses don't really change a whole hell of a lot, do they? They're pretty much the same across the board. And so I want you to justify the trend in boiling point based off of the intermolecular forces experienced between these 5 molecules here. And that is it for the data sheet. So the data sheet might seem a little longer than some of the other data sheets with the 3 questions. However, the lab doing the correction for the refractive index is pretty quick, and identifying the unknown usually gets done with, I'd say, a high degree of confidence, or a high degree of correctness, I guess, for lack of a better way of explaining it. Let's see. Are there any questions? I'm trying to think if I left any stone unturned here. Any questions at all? Lauren, are you there? Do you have any questions? All right. No? Okay. Well, if there's no questions, I feel like I covered everything in gross and gory detail here. And of course, again, I expect you to, where am I here? I expect you to do the reading, which I don't know where I had it, but I expect you to read all the background. So technique D, Technique E, you need to have that knowledge before you step in the lab. And I need you to read 3.2 and 3.3, the whole thing, so that you're totally prepared when you come into the lab. And again, I left a couple things for you to discuss with your lab instructors, but I think I covered all the necessary points there. Okay.